After years of anticipation, the James Webb Space Telescope (JWST) has finally delivered on its promise by observing deeper into the universe than any previous human-made instrument. For the first time, scientists have captured light emitted from galaxies that formed just a few 100 million years after the Big Bang, structures so ancient that their light has traveled across space for more than 13.5 billion years. This achievement is far more than a technological triumph. It provides a direct glimpse into a time when the universe was still in its formative stages, cloaked in primordial gas and shaped by the delicate dynamics of early cosmic evolution. What JWST uncovered at this extreme boundary of the observable universe challenges established scientific theories, adjusts our cosmological timelines, and signals a transformative era in space exploration and understanding. The James Webb Space Telescope was specifically engineered for discoveries like these. Unlike its predecessor, the Hubble Space Telescope, which focused primarily on visible and ultraviolet wavelengths, JWST operates in the infrared spectrum. This capability is essential because light from extremely distant galaxies becomes redshifted as it moves through the expanding universe, shifting it into longer wavelengths. By the time this light reaches Earth, it exists in the infrared range, making JWST the ideal tool to observe it. What the telescope revealed were not merely faint traces or barely visible smudges, but fully formed galaxies, massive, structured systems that came into existence far earlier in the universe's timeline than scientists had predicted. These early galaxies exhibited surprising levels of organization and complexity. Their structures were more mature than expected, with defined shapes, significant masses, and high rates of star formation. The light captured by JWST originated from a time less than 300 million years after the Big Bang. In cosmic terms, that's a blink of an eye. Previous theories held that galaxies would not begin to form until at least 400 to 500 million years after the Big Bang, and that the earliest ones would be disordered, composed mainly of hydrogen and helium. Contrary to these expectations, JWST found galaxies already enriched with heavier elements, those formed in the cores of stars and dispersed by supernovae. This implies that not only had stars formed quickly, but some had also lived and died, contributing to chemical complexity much earlier than previously thought. The implications of these findings are profound. The presence of mature galactic structures so soon after the universe's origin suggests that cosmic evolution progressed far more rapidly than models had indicated. This has led scientists to reconsider the conditions of the early universe and the mechanisms driving galaxy formation. Were the first stars far more massive and short-lived than once believed, hastening the cycle of stellar birth and death? Did dark matter play a more significant role in shaping galaxies than previously assumed? Some of these early galaxies appear to be as massive as the modern Milky Way, providing critical data for new theoretical models. In addition to galaxies, JWST also detected regions dense with gas and dust, clear evidence of active star formation. Thanks to its infrared instruments, the telescope was able to peer through clouds that had previously obscured such regions, revealing stars in the act of forming, woven into the vast cosmic web that stretches across the universe. Though previously theorized and partially observed, this web came into clearer focus under JWST's observations. It showed glowing filaments of matter connecting galaxies, illustrating the universe's large-scale structure as it began to emerge. Another remarkable observation was the detection of gravitational lensing caused by massive foreground structures. As light from background galaxies passed near these massive objects, it was bent and magnified, revealing otherwise invisible features. This natural lensing allowed JWST to see even farther into the universe's past, uncovering faint proto-galaxies, early accumulations of matter just beginning to take shape. These glimpses into the universe's formative stages are not only scientifically important, but philosophically significant. Observing the edge of the observable universe means looking at the farthest reaches of time and space that we can perceive. It's not the boundary of all existence, but the limit to how far light has traveled to reach us since the universe began. Yet by approaching this limit, JWST has allowed humanity to piece together the earliest chapters of the universe's story. These observations also raise critical questions about the universe's expansion. The redshifts JWST recorded not only confirm that space is expanding, but also provide a new level of precision in tracking how that expansion has changed over time. If the early universe expanded faster or slower than current models suggest, it may indicate that dark energy, the force believed to drive this expansion, changes over time, potentially rewriting key principles in modern physics. Moreover, the surprising mass and density of these early galaxies offer new insights into dark matter. The standard cosmological model assumes that cold dark matter was essential for the formation of cosmic structures. But with galaxies appearing earlier and more massive than predicted, scientists may need to revise their understanding of how dark matter behaves and interacts with normal matter. Is it possible that dark matter is more complex than assumed? Or might there be unknown components in the cosmos yet to be discovered? These questions now define the forefront of theoretical physics, fueled by JWST's data. Perhaps most profound is how these discoveries challenge our perception of time itself. The galaxies JWST observes are not just distant in space, they are distant in time. Their light has traveled for over 13 billion years, meaning we are seeing them as they existed just hundreds of millions of years after the Big Bang. In essence, JWST acts like a time machine, allowing us to witness the universe as it was in its infancy. All of our known history, including the formation of our solar system and life on Earth, came long after these galaxies were born. To witness their ancient light is to feel connected to a timeline that stretches unimaginably far back. The telescope's instruments have also been able to analyze the spectra of this ancient light, revealing the chemical compositions of these early galaxies. Elements like carbon, oxygen, and nitrogen, key building blocks of life, were found much earlier in the universe's history than previously expected. Although this doesn't prove the existence of life, it suggests that the raw materials needed for life may have been available in some parts of the universe within its first billion years. If planetary systems formed early enough and had access to these elements, the potential for life in the early universe cannot be ruled out. Beyond the scientific data lies a deeper, existential truth. Through JWST, humanity has gained a perspective that was once unimaginable. It allows us to see the universe not just as it is, but as it was, a place of dynamic creation, rapid evolution, and complex processes unfolding long before our existence. The light captured is more than information. It is a record of cosmic memory encoded in photons that have traversed billions of light years to tell their story. This moment also represents the beginning of a new era in space science. While previous telescopes mapped stars and planets, JWST has moved beyond that into the realm of the primordial unknown. It has extended our observational reach to the very threshold of what is detectable, and just beyond that threshold lies a universe still waiting to be discovered. The edge of the observable universe isn't the end of the story, it's the beginning of another chapter. The galaxies JWST has captured are no longer isolated relics, they are part of our shared cosmic ancestry. Their history is intertwined with ours, and each new discovery adds depth and complexity to that shared story. As the telescope continues its mission, it will return data from even more remote corners of the early universe, data that will continue to challenge current models, inspire new theories, and expand our understanding of reality itself. The edge it has reached is not a final limit, but a dynamic frontier, inviting us to explore further. The universe, once silent and unknowable, now speaks through the ancient light JWST has captured, revealing secrets of beginnings we are only beginning to comprehend. JWST is not merely taking snapshots of distant galaxies, it's transforming our understanding of cosmic history. Its high-precision infrared instruments allow astronomers to analyze early light in unprecedented detail, examining subtle variations in brightness, composition, structure, and temperature. This level of detail is redefining what we mean by the edge of the observable universe, painting a richer picture of its earliest moments. Among the telescope's unexpected findings was the discovery of densely clustered ancient galaxies in what was assumed to be a sparse, chaotic region of spacetime. Instead of isolated fragments, JWST found a dynamic field teeming with galactic interactions, mergers, collisions, and distortions happening much earlier than theoretical models had anticipated. These interactions would have accelerated galactic growth, led to earlier black hole formation, and shaped the cosmic landscape in dramatic ways. Further analysis revealed signs of early black hole activity. Quasars, intensely bright sources powered by supermassive black holes, were already present a few 100 million years after the Big Bang. This discovery challenges standard theories, which hold that such massive black holes should take billions of years to form.